don't know if we want to. So it's 9:01. We can wait another minute. So Henry and Spencer, do you guys want to? One of you guys want to share your screen at some point? How do you want to? Are you going to?
Yeah, just give us the go ahead of when you want us to start, Mike.
Okay. Why don't we wait one more minute, 9:03, and we can get started. All right, one of you guys want to share your screen and we can get started?
Yeah, I'm gonna go first, and then after my presentation, Henry will go. Let's see. All right. Switch this. Okay. Do you see the full screen version?
I do.
Great.
And
What?
we can even hear you.
Wow, perfect. Okay. So I am going to be, Henry and I are going to be talking about this collaboration that we've been working on, looking at the effects of static order disorder on their impacts on conjugated polymers. I've been kind of tackling this from the electrochemistry side, and Henry has been working on it from the spectroscopy side. So my half of the presentation is going to be more electrochemistry focused, just as a heads up. So the two types of polymers that we are working with are P3HT and PBTTT. They differ in their morphology, with P3HT being semi-crystalline and PBTTT being more of liquid crystalline. There's these two kind of schematic representations of what these kind of look like at like what their morphologies look like. And there's like a kind of a way of describing it of being spaghetti-like for P3HT in terms of having long interconnected backbone for charge transport to occur. And then PBTTT is more rice-like, where it has this kind of shorter order in its backbone to facilitate charge transfer. Now, I don't know, is there anything you want to correct me on, Henry, with that?
Yeah, so I guess the main reason that we're interested, I guess, in comparing disorder in these two classes of polymers, so I guess here we select P3HT and PBTTT as, like, I guess, classic example of flexible chain in the case of P3HT, and hairy rod in the case of PBTTT. Hairy rod, I mean having these fused moieties in the backbone, as long as the long side chains comparatively compared to P3HT, which collectively give you this liquid crystalline-like microstructure. And I guess the point that we want to emphasize here is that kind of our working hypothesis is that in these liquid crystalline-like polymers, you create something that is, I guess, let's say, microstructurally more homogeneous, because whether you pick a point in kind of your microstructure or PBTTT, no matter where you are, you're in this kind of liquid crystalline-like phase, and locally you feel more or less the same environment, versus in a semi-crystalline flexible chain polymer, where whether you're in a crystal or whether you're in the amorphous region, that local environment of your polymer is very different. So we hypothesize here that this should vastly increase, I guess, the degree of static disorder in your flexible chain polymer as opposed to your liquid crystalline-like hairy rod polymer, which we hypothesize, so I guess structurally we know is more homogeneous. And I guess now what we're trying to do, both chemically and spectroscopically is to link that structural disorder with the electronic disorder, whether that's through electrochemical or spectroscopic methods. So yeah, go ahead, Spencer, sorry.
Okay. Yeah, so to kind of start looking at that from an electrochemical standpoint, I did some macro scale electrochemistry, i.e. made a polymer film and just did kind of like the standard type electrochemical cyclic voltammetry experiments. And so this is what these two kind of CV responses between the polymers look like, with this being P3HT and this being PB-triple-T. And the thing that I kind of want to kind of maybe highlight here is that the macro scale electrochemical response is a kind of like a summation of all of those microstructural contributions to the current response of the polymer. And in doing these macro scale measurements, there's a lack of spatial resolution in the density of states of the polymer. So you can get a kind of ensemble density of states from this measurement, but you can't get maybe more localized density of states. But the thing to kind of highlight here is that in P3HT, we see two kind of redox events. One here at a lower anodic potential and one at a higher anodic potential. And this corresponds to the crystalline regions of P3HT being oxidized and then the amorphous regions of P3HT being oxidized. In PB-triple-T, we see one kind of redox event, and that's just the there's no real crystalline or like amorphous phase in PB-triple-T. It's more of just that liquid crystalline phase. And so that's what we see here when we oxidize. We just see one kind of singular redox peak.
So what's the electrolyte here?
The electrolyte here is 50 millimolar tetrabutyl ammonium hexafluorophosphate in propylene carbonate.
And have you tested that hypothesis with other electrolytes?
I've done it in acetonitrile, but I'm using propylene carbonate in this set of experiments because it's an easier electrolyte to work with when moving to the nanoscale electrochemistry measurements.
But presumably you see comparable behavior in acetonitrile.
Yes, exactly. You see
Okay.
comparable behavior.
Okay, thanks.
Yep. So again, this is at the macro scale, but then how can we start answering these questions at maybe the nanoscale? And this is where kind of the technique that I've been working a lot with, scanning electrochemical cell microscopy, comes into play. Just as like a brief highlight, I think I went over this a while ago, so I'll just briefly go through this. But there's a pulled capillary that's filled with an electrolyte that you can use to control the size of the electrolyte meniscus, which in turn controls the size of the working area that you're measuring. Sample, in this case, acts as the working electrode, and then a chloridized wire is inserted into the capillary to act as a quasi-reference counter electrode. So you can do these kind of measurements, these kind of three, or these, you could do these electrochemical measurements at the nanoscale. And so I did this on both the P3HT and PB-triple-T. And these are kind of the responses that you get when you overlay all of the recorded CVs. So there's 441 CVs recorded in each of these measurements. And when all of them are overlaid on top of each other, in P3HT, you can see that, you know, when we're not in the areas where we saw, you know, some kind of redox behavior, the CVs are overlaying very nicely. That's why there's this very, very dark line. But as we start oxidizing our polymer, when we get to the crystalline region, there's still some overlay, but you can see that the line is kind of broadening. And then as we get to the amorphous region, again, we see lots of kind of distribution in the current response. Whereas in PB/TTT, all of the CVs are overlaying very, very nicely. And so this is just an overlay, but what we can do with this is take kind of these regions of interest. So these red circles indicate at least regions of interest of where we can grab a current and plot it as, instead of histogram, to see what the distribution of those currents look like. And so when we do something like that, we can get a histogram that looks like this, where the amorphous domain of P3HT has this really broad broad in comparison to the crystalline and to PB/TTT's current response. So there is some distribution in the current that we see from these polymers at the nanoscale. So there's clearly some impact that the morphology is having on the current response we're seeing. So this is just current response. But what we can also do is approximate a density of states from the CV at both the macroscale and nanoscale and do some comparison there. And so that's the next thing that I'm going to highlight. In P3HT, if we do this density of states approximation, we can see there's two kind of regions where we have this where we have a higher density of states, kind of here, which is again corresponding to the crystalline region and then to the amorphous domain. Whereas PB/TTT has this very sharp density of states compared to P3HT. So P3HT is more broad in its locations of its density of states, whereas PB/TTT is more has this very sharp density of states feature. And then if we move to the nanoscale approximation of the density of states, you could see that P3HT has, all these lines aren't necessarily overlaying perfectly on top of each other. So there is some kind of spatial heterogeneity in those density of states, whereas in PB/TTT, all of the states are overlaying kind of nicely. So kind of the take-home message here is that P3HT has kind of a broader distribution of density of states that could be tied to its microstructure, whereas PB/TTT has a more narrow distribution density of states. I'm still trying to find a way to, put something like this into a histogram. So if you have any thoughts on that, please let me know. And then just as kind of a side discussion of some other things I've been doing, is also looking at charge transfer kinetics in these systems. So if you add ferrocene to your electrolyte, you can see kind of a mix of the ferrocene redox peak and the kind of response from the polymer. And I'm changing the colors of my graphs here because I started using, at least in these studies, I'm using a different type of P3HT and PB/TTT. So if I do the same sort of measurements at the nanoscale, again, you see kind of this overlay of the current response from the polymer and the ferrocene redox peak. And what you can do here is approximate the rate constant of electron transfer using a Butler-Volmer approximation. In this case, I do want to kind of acknowledge that Butler-Volmer approximations are not necessarily correct for conductive polymers and for semiconducting systems in general. But I'm doing this mostly as a first approximation, and then can use it as a comparison for a more robust rate constant approximation technique. The point is, I can take my nanoscale CVs, fit them, and obtain the rate constants. And kind of what I get from that is P3HT having a slower rate of electron transfer and kind of a broader distribution of electron or rate constants, whereas PBTTT has a relatively higher or faster electron transfer rate constant. And because these measurements are taken kind of spatially, you can also make a map of the rate constants in these samples. And so that's what these kind of pictures on the left and right are showing. And so this is what I've been doing from the electrochemistry side, but then Henry has been kind of taking this on from the spectroscopic side. So this is kind of marking the end of my half of the presentation, and can pass it off to Henry.
Can I make a comment?
Yes.
I don't know if Neil's on the line, but you know, one of the things that was noted about ITO is that a lot of ITO is dead, and then there are hotspots where a lot of current goes through.
Yes.
And I'm looking at your graphical image, and certainly the PBTTT is much more homogeneous, but one of the things that I think you can see with the P3HT is that there are at least some hotspots, right? Yeah. And a question that I'm curious about is, if you're doing electron transfer, you know, is the majority of your current going through those hotspots when you have a sample? And if so, you know, what might be the consequences of that in terms of ultimately what the achievable rate is? I mean, you may be just sending a lot of current. Your average rate may not be the most important thing. Your peak rate may be the most important thing. But from that perspective, and this is something that goes back to LED work back in the day, is that some of the challenges that I think people found with ITO in the early days of OLEDs is that when you have a huge amount of current going through a few spots, you have a lot of resistive heating, and that resistive heating seemed to be a place where things like delamination and damage occurred. So I'm not sure if this was some of the motivating factors to sort of do this imaging, but this imaging may provide insight that can be used to not only relate to just the fundamentals of what's going on, but from which you might begin to think about either experiments that relate to durability or whether we should even be worrying about it.
Yeah, I think that's definitely, I do know that ITO does have the hotspots. I didn't think about it in terms of how this would impact, you know, the regions of the film, but I do see how there are, you know, hotspot kind of, I guess, quote, hotspots in my rate constant plots. But I think one thing that I could maybe do to see if that's related to the ITO itself is maybe using like a metal, like depositing my film on a metal electrode that has a, more homogeneous current response compared to P3HT. And that might be a way to see if this is something related to the P3HT to the ITO, or if this is just like something that we see in P3HT in general. But I think that would be interesting to look into.
Spence and says, actually, I have a question here too. So how actually do you determine or identify the hotspot before actually you casting your thin film?
That is something that I don't know if you can necessarily find the spots ahead of time forecasting the film. I mean, my first thought is you could measure P3 or ITO and see kind of what the maybe density of hotspots are to make an approximation of what they would be, if that holds true across the whole piece of ITO. But I think that's the only way you might be able to get towards determining the amount or location of hotspots in ITO.
Says, do you actually have an idea, how generally people will characterize actually the hotspot, in advance?
Well,
it will be too late actually after actually you cast the same film, right?
Couple of quick comments. You're raising something that I didn't even consider, and that is that the hotspots he's seeing in the P3HT are actually due to the ITO. And I didn't consider that because in part because if that was what was governing the hotspots, I would expect to have seen that in the PB/TTT as well. So in other words, if the underlying electrode was what was governing it, and some of the homogeneity of the PB/TTT would have modulated, or it would be modulated by the hotspots. On ITO, I believe that first of all, the ability to actually create those hotspots, I think, is not well understood. And I would say was a topic of consideration for another EFRC. Characterize it, I think that, which was not funded, by the way. To characterize it, I think that you do the kind of experiments that were done here.
You can characterize it doing similar, electron transfer, except it would just be on a bare ITO, and you would get these kind of rate constants and make a similar map and see where it's fast and where it's slow. And that's work that has been done before. There's a paper out about that, but that's one way that you could get towards answering those questions.
See, Mike has patiently been waiting.
Yes. So as I understand it, the tip radius is 500 nanometers. Is that correct?
Yes.
So what's your
the tip radius is 250 nanometers. The diameter is 500.
Okay. But the sensing area, then, do you know what area you're measuring over?
So that the kind of approximation of the area is, at least in literature, said to be about 1.2 times the diameter of your tip.
So let's just say 600 nanometers for the sake of argument.
Yeah.
The domains, right? The chrysolite size in P3HT, right? So the size that's associated with either the amorphous or the crystalline regions tends to be a lot smaller than that, at least in order of magnitude. So, but as I understand it, you're interpreting this as being from the maps as being from amorphous domains and crystalline domains. But aren't you averaging over like 100 domains?
Yeah, so I wouldn't say that I wouldn't say that I'm attributing this to being exclusively crystalline or exclusively amorphous, but what I would say is that in the areas that have maybe a higher rate constant, I would be maybe incorporating more of the crystalline domains, and that might be a reason why the rate constant is higher in those regions, because it's incorporating more than other sampling areas. But I mean, my tip size is, in this case, it's 500-ish nanometers in diameter, but there is no reason why I can't go lower. People are using this technique with pipettes that have diameters of 50 nanometers, and they're doing it successfully. It's just a matter of optimizing the pipette recipe to get it smaller. But this is kind of again, kind of a proof of concept, first time using this this technique in our lab to try and get towards some of these questions. So
No, yeah, I mean, the results are super interesting. So have you looked at different regional regularities or even regional random P3HT just to see if you see this, I guess, I don't remember, the right side peak go down with more amorphous regions?
no, I haven't, but that's something that, you know, I could start working on.
Yeah, that certainly would, right, help support this. Okay, cool.
Definitely.
Thanks.
Yep.
Thanks.
All right, Henry, do you want to take over so that you have some time? Okay. Stop sharing.
Okay, so yeah, I guess to piggyback off of Spencer's work, let me get this going. Yeah, so I guess the main tool that I'm going to be talking about is 2D spectroscopy. And I guess the main idea here is kind of from what Spencer showed in his work, we see this very tight distribution of the density of states of PBTTT compared to a very broad distribution of the density of states in P3HT. But I guess we attribute that, I guess, to both structural and electronic disorder. And here, I guess, in my work, what we're trying to do is to really separate, I guess, the nature of that electronic and structural disorder using 2D spectroscopy. So as a, to advance, here we go. So I wanted to give, I guess, a brief background on what 2D spectroscopy is, because I know it's a technique that not a lot of people tend to use. And essentially, I guess the main thing that I want to understand from this is that 2D spectroscopy is an excellent technique at disentangling, I guess, the relative time scales of, let's say, fluctuations or disorder in your system. So if you take consider your system being, I guess, the Hamiltonian of maybe that thiophene unit on your P3HT or PBTTT backbone, and what are the contributions from these fluctuations of this fluctuating dielectric environment, different vibrations, phonons in your system, and how can we separate those effects on the system of interest? So we see this really spectroscopically, I guess, in the absorption or the PL line shape that you observe really in any spectroscopy, right? So if you think of like the linear absorption and the PL line shape of P3HT, PBTTT, we know that most of those are highly broadened. They look quite blobby, one might say. And this linear line shape that we observe in typical spectroscopy is really the convolution of this homogeneous and its inhomogeneous line width. So by this, I mean this homogeneous line width is related to fast fluctuations of your local environment, and this kind of dynamic disorder. So that which occurs on here, the time scale of our pulses is on the order of around 20 femtoseconds. So fluctuations that are on this time scale versus this inhomogeneous line width is due to primarily slow fluctuations or static disorder in your system. And in typical linear spectroscopy, you cannot deconvolute these two types of disorder. So really what you see is a convolution of both. But in 2D spectroscopy, we use these series of ultrafast pulses. And by looking at the correlation between two distinct energy axes, which is we get from a Fourier transform along these tau1 and tau3 axes, we're able to separate these two, right? So we can tell you what is the, I guess, the relative magnitudes of disorder that comes from static and dynamic disorder. So as I guess many of you may be aware of previously, I guess a lot of the work that has been done on conjugated polymers with 2D spectroscopy has really, I guess, shown that in most cases, flexible chain polymers, which are those which have been the ones that have been primarily studied using 2D spectroscopy for, I guess, historical reasons, are typically largely inhomogeneously broadened. So this inhomogeneous line width, I guess I didn't do a good job of explaining this, comes from more or less, you can think of this inhomogeneous line width as taking a cut along the diagonal of your 2D map, and your homogeneous line width you can think of as taking an anti-diagonal cut, so these purple circles on your 2D map, right? So if you look at just P3HT from back in the day, we can see that really this line width that we observe in the 2D map is strongly inhomogeneously broadened. You see almost no features along this diagonal because of that strong inhomogeneous broadening, right? So from this, we started to look at the case of PBTTT to try to understand that in this situation where we think that we have less static disorder due to this local homogeneity, how does that affect this interplay between static and dynamic disorder? And long story short, what we see in the case of PBTTT is a highly dynamically disordered energy landscape. So here what you're seeing on this top graph is the just linear absorption line shape of PBTTT, where you see your 0, 0, your 0, 1 transition. And again, like I was saying, this highly broadened line shape. But again, you cannot separate what is static and what is dynamic from that. And if we look at this 2D line shape, you can think of like expanding this onto 2 dimensions, that line shape. And you see here along the diagonal, your 0, 1 transition, your 0, 0 transition. And like what you see in the linear line shape, the much more intense 0, 1 transition, as well as these correlations on the off diagonals, which tells you something about these correlations between these excited states, and that essentially they're sharing a ground state. But I guess the most important thing here that I want to highlight is that if you look at this anti-diagonal versus the diagonal cuts along the 2D line shape, you can see that just by eye, they're clearly of similar magnitude, and that we're not in this strongly inhomogeneously broadened regime. In fact, if we fit this, we find the homogeneous line width to be around 40 millielectron volts, and this inhomogeneous line width to be around 18, 20 millielectron volts. So here we're clearly in this I guess region where we have this competition between the static and dynamic disorder, or this inhomogeneous and homogeneous broadening. So from this, I guess the question that we want to answer is like, what is the nature of this dynamic disorder, and what is leading to this strongly homogeneous broadened system? So to do this, what we do is we look at the time evolution of this 2D line shape. So essentially, we will vary the evolution time between this tau2 and let our system evolve in time. And what we do is we plot the intensity of the 0, 1 transition as a function of that population time. And from this, we observe that this more or less, you can think of it like a damped sinusoidal function that describes essentially the intensity of a 0, 1 transition. And in seeing this, we decided to fit it to this damped sinusoidal function to get kind of the frequency of this oscillation of that 0, 1 transition. And we found that to be on the order of around 72 femtoseconds, or if you convert that to be around 465 wave numbers. So from this gives us, I guess, gives us some insight on, I guess, the relative timescales of these dynamic fluctuations. And then we went further to try to understand, I guess, what do these fluctuations correspond to, let's say, structurally. And from this, we did resonance Raman spectroscopy. So as we all probably typically know as well, typically your resonance Raman spectra is dominated by these higher energy or wave number modes, which more or less I'm showing you them here simulated for this PBTTT, I think, trimer without the side chains for simplicity. But what we found was that this low frequency mode, which again corresponds to this mode that we found from the 2D spectroscopy around 465 wave numbers, corresponded to I guess a unique mode, which is that of this combined twisting of the polymer backbone combined with this stretching or strong stretching of the thionyl-thionephine unit of the backbone. And this, I think, we contextualize in the context of, I guess, the typical fluctuations of hairy rod polymers, in that typically in the liquid crystalline system, you form a very low entropy system due to the, I guess, these side chains kind of locking in this backbone. And as a way to increase entropy, oftentimes these systems will tend to undergo these kind of segmental twisting motions to help increase entropy in the system, which is what we see, I guess, from correlating the frequency of this mode to kind of the structural motions of this mode as well. But so yeah, I guess this gives more insight on like what is these structural parameters that are driving this dynamic disorder, right? So now, having this understanding of PBTTT, we went back to P3HT to this previous data that I showed you from 2015, was using a different implementation of 2D spectroscopy, and also the processing was slightly different. So we wanted to repeat this using the same variation of 2D spectroscopy and be able to nail this down correctly. And long story short, the story I think is a little bit more complex than what we originally thought. And if you saw my poster last week, this was missing some data that we got actually a week and a half ago that I think kind of throws a wrench in this story. So bear with me here. So what we see when we implement this new, implement this same version of 2D spectroscopy on P3HT is actually a line shape that actually strongly resembles what we saw of the PBTTT as well. So again, you see these from our linear absorption line shape here in black. When we look at this on the 2D map, we again see this strong 0-1 transition, a weaker 0-0 transition, as well as these cross correlations between those two on the off diagonal. But unlike what we saw previously, we again are in a regime of a competition between this static and dynamic disorder, quite similarly to what we saw with PBTTT. So if we compare these side by side, we can see just, let's say visually for now, that this competition between dynamic and static disorder seems to actually be comparable in at least this measurement of P3HT. So this, I think I'm still really trying to understand, and I would really appreciate others' input on this. My current working hypothesis, I guess, for why this might be the case, I guess, are kind of threefold, especially in the context of if we think of Spencer's data from, at least electrochemically, we see this very tight distribution of the density of states in PBTTT versus this wide distribution in P3HT, indicating that at least with this electrochemical probe, we see this high degree of static disorder. However, spectroscopically right now, what we see is something that is of a comparable competition between static and dynamic disorder as we saw in PBTTT. So I guess one proposition could be that here in 2D spectroscopy, perhaps the length scales at which we're probing this disorder are different than that of these electrochemical methods. And then I guess to understand this versus previous implementations of 2D spectroscopy that have measured P3HT is that these oftentimes can differ slightly in kind of the coherent pathways that we use to observe the signal. So perhaps that is giving rise to some artifacts in the data that we see. And finally, I guess this specific P3HT that we're looking at here is, I guess, tuned to be somewhat more J-like in its in aggregation. You can see a pretty strong 0-0 transition here. And whether this kind of local ordering that we induce by processing it in this way is really changing kind of this energy landscape as well. So yeah, I guess this leads us to kind of the different energy level distributions for these classes of polymers, which I again presented last week, you may have seen. But I think now we need to kind of reassess as well. So from, I guess, in the case of PBTTT versus, let's say, a inorganic semiconductor, you would have in an inorganic semiconductor, let's say, a very well defined energy level distribution, right? Much like a band-like structure. And what I showed you in the case of PBTTT, I think was quite convincing that here we have a lower degree of static disorder, as well as some comparable, let's say, magnitude of this dynamic disorder, which are dynamically influencing this energy level distribution. However, in the case of P3HT, I guess our original working hypothesis was that the nature of the magnitude of this static disorder was much larger than that of this dynamic disorder. But really, I think right now we still need to kind of wrap our heads around these differences that we see electrochemically and spectroscopically as to perhaps P3HT actually lies somewhere in between these two, or whether or not this is reproducible, I guess, is another question as well. So yeah, I guess that brings me kind of to the end of my talk. I'm sorry that it was not as conclusive as I would like it to be, but I would be happy to have a discussion on this. So yeah, please let me know.
Hey, go ahead, but I'll be patient.
Thanks.
Yeah, thanks, Henry. This is really neat. And maybe, well, first question that came to my mind is maybe one that not everyone needs to hear the answer to, which was I was curious about the differences in implementation you're talking about, since I presume in both cases you're talking about a photon echo detected 2D experiment.
Yeah,
But-
so maybe to give the brief answer, and we could talk more offline if you're interested too. This previous data that I showed you on P3HT, the original one from Felix, this is using a implementation where you actually detect the signal incoherently, and you use lock-in detection to kind of isolate the coherent part of your signal. And what we've shown, I guess, in our group as well is that actually that specific technique is often prone to kind of incoherent artifacts. And in the case where you have highly mobile photocarriers, these incoherent artifacts can actually dominate kind of the response that you see in your 2D line shape. Previously, we showed that in semiconductor polymers, P3HT is actually at low temperature, that these kind of non-coherent incoherent mixing effects were negligible. Versus what the technique that I'm using now is kind of in the traditional boxcars geometry, where we're directly interfering a local oscillator with those other three pulses, and we're kind of directly measuring that coherent signal. So I would say that in this implementation, probably we're better at isolating that coherent signal in which we're interested. But yeah, the main difference is in the way that we detect the coherency.
I see. And the other sort of question / suggestion I had was, I'm thinking back to long ago when my first project as a postdoc was working with Natalie and Gary, looking at different molecular weights of P3HT. And you know, there's obviously really different behaviors, but one of the things that jumped out of that I've not really done much with after that was that the thing that was most different in terms of seemingly having much higher order was a pellet of P3HT that had been pressed. And I just wanted to suggest that as a potentially very interesting point of comparison.
You mean to use this as kind of as opposed to a crystalline polymer, something that is also very one phase?
Yeah, you get something that seems to be much more crystalline, has much less of the amorphous regions, we thought, when you do the solid state processing.
Yeah, certainly. Yeah, I guess, yeah, in that case, probably you would produce something that is the most, I mean, it's never going to be fully crystalline, right? But the most crystalline that you would get versus something that's solution processed. So yeah, that's a good point, actually.
Go ahead, Gary, you had your hand up first.
No, I didn't, Mike. You did.
Well, I'd be okay, sure. Great. So thanks. This is very, very interesting. Have you cooled down, right? So you have this hypothesis on the difference between static and dynamic disorders. It seemed to me that the natural way to do this would be just cool thing down to 77 and check, because the dynamic disorder should all freeze out, or basically, well, not freeze out, but should go away under those circumstances.
Yeah, so yeah, I guess one thing that I brushed over here, both of these measurements are done at 10 Kelvin. They're both at very low temperature. So even, I guess, at 10 Kelvin, you see this, I guess, dynamic, I guess, yeah. You see the clearly dynamic disorder in PP-T.
How are you exciting the phonon mode at that high in energy if you're at 10K, which is like two, like a 1 MeV or something like that?
Yeah, I guess that's a good question. I interpret it as, I mean, here these are very low frequency and I guess low energy modes, right? Where here we're, I guess, at around this
I
most
guess that-
and
okay.
then it's around 465 wave numbers.
Yeah, what is that at MeV? I can't think of wavelength.
I
can only
don't
think
know
of
off the top of my
MEVs.
head,
Okay.
actually. It is something I should check.
Okay. Do you know how that compares to RT?
Yeah, that is something that I should report, actually, and I don't know off the top of my head.
Mike, I think it's just above room temperature.
Okay.
Room temperature RT is 200 wave number, more or less.
Hmm.
So you are right. So you're exciting a mode right at 10K that is got an energy of like room temperature.
Yeah,
It seems,
that's
seems a little weird.
Hmm.
And I guess then have you done higher temperature measurements even like because again you should see something if you go to higher temperatures that would induce more of the phonon modes?
Yeah, so we have, I guess, part of the reason, I guess, that we cool down, like I was mentioning earlier, which I guess is less of a problem in this specific implementation of 2D spectroscopy, is that based on a kind of like let's say the mobility of these photocarriers, sometimes your signal can be, this coherent signal can be dominated by these incoherent mixing effects, which are more dominant, I guess, the more mobile those photocarriers are. So typically we cool down to be able to really isolate what is these coherent effects that we're interested in versus what you're seeing in these incoherent effects is really just nonlinear population dynamics, which is not at all interesting, I guess, in this context. So
even just go ahead.
Yeah, so I think what we've seen, I guess, in the case of most conjugated polymers that we looked at in our group is actually that the line width is highly insensitive to temperature. So as we cool down, this inhomogeneous line width is relatively constant. And that's what we've seen in probably at least 4 or 5 different conjugated polymers now at this point.
So how's that consistent with kind of this concept of dynamic disorder, which is, at least as I understand it, the implication is that's thermally induced, so there should be a temperature dependence to this.
Yeah, so I guess, so first of all, I guess the point that the inhomogeneous line width related to the static disorder should be independent of temperature, to me, I guess, more or less makes sense in that if you have some distribution of, let's say, local ordering of your polymer, as you cool down, you're just freezing those in place. And you're at 10K, you really have the same thing that you started with at 295K if you had some distribution of energies, right? I guess rationalizing that in terms of this dynamic disorder and its, I guess, its energetic barriers is something that I should probably think more about.
Yeah, I would encourage you to do that because certainly the picture you're literally showing on the slide is some kind of vibration, which has to be thermally induced, right? It will stop being relevant if you're at low enough temperatures that you can't actually drive any of these.
Yeah, I mean, I guess, yeah, I mean, I first thought, I mean, I would say that here, I mean, these are photo-excited though, right? So that, I guess these electronic and these vibrational transitions are also linked, right? So I guess you're inputting energy as well from the photon as well, right?
Yeah, okay, that's a good point.
You're putting in a lot of energy.
Yeah.
Okay, cool. Thanks. That's a good comment. I hadn't appreciated.
Thank you, Mike.
Yeah, I would like to comment here. So
Sure.
You don't have to thermally excite a mode if it's dynamic, because quantum mechanically vibration happens at 0 temperature. So if you look at dynamic disorder, and we did this as function of temperature when we calculate, so then about 60% you can see at low temperature of the mode. It's of course constant with temperature, then it starts to go exponential if you go to high temperature, but this is the manifestation of quantum or quantum nature of vibration. This is what you take high frequency vibration, you treat quantum mechanical at high temperatures, but now the low frequency mode became quantum mechanical at low temperature. So they will still contribute to the broadening.
Mhm.
Yeah, but there still will be a temperature dependence. Certainly, the zero point
right.
motion matters, but there's a thermal contribution as well, right? It can't be constant in temperature.
That's right. It will be a range of temperatures where the temperature dependence is extremely weak, and at some point it starts to go exponentially. But I would say 10 Kelvin up to 150 Kelvin, you'll see no change as function of temperature. It will be minor.
Yeah, but that depends very much on the mode energy, right? And the details.
Right. So I'm saying for 400 wave numbers, that will be.
Mhm.
I have actually a question. So you look now at the high energy transition, let's say about 2 electron volt, right?
Yes.
But this disorder will be mostly related to exciton transport, not to charge transport. So if you want to understand disorder related to charge transport, then you will have to probe a transition that appeared due electron or hole transport. So has anyone used this technique to look at this, or is a way to do that?
You're talking about looking at, you mean like polaronic transitions?
Right, because you need that charge is moving.
Yeah, I guess that's a good point. Certainly 2D IR exists and is probably actually the much more well-developed field than in the visible. But I don't think that it has been, at least at this point, actually at all applied to kind of polaronic transitions in conjugated polymers. Typically, I guess it can be somewhat challenging to do in the presence of solvent and electrolyte, just because, yeah, I won't go into the details here, but experimentally, it can be slightly challenging. But yeah, it's a good point that here we're really looking at the exciton versus electrochemically, and what we see with Spencer's work is the polaron. I guess the working hypothesis was that those were linked, but I guess you're correct that perhaps this disorder that we see of these excitonic systems may have differences from that what we see once we are looking at exciting the polaron. So
thank you.
Mm-hmm.
Gary.
Yeah, I have a question. I'm going to go back to Spencer, if I may. My questions have all got muddled up because they've all been partially addressed by other questions that have popped out. But one that comes to mind when you're doing the electrochemistry on a film that is 100 nanometers thick, one thing that's kind of important for specs is how far into the film, and you were knocking on the door of this, Mike Tony, how far does the counter ion, the supporting electrolyte, get into the polymer film? It seems to me that that's a super important question for us to address, because if we're thinking that it's nothing, then that's one extreme. If it's a little bit at the surface and nothing in the bulk, then that's a different thing. And there is a really nice paper that I can't find immediately, but I keep asking. Obadiah will know which paper I'm talking about, where they made ultra thin films by floating the sample on water and then lifting it off onto an electrode, and that enabled them to do really, really good cyclic voltammetry, and where they were quite convinced that the electrolyte ions were getting into the film. So I don't know how I don't quite know how this all fits together. And then my last part of the question is I was expecting the 2D spectroscopy to actually look at the same films under charging conditions. But if you're at 10 Kelvin, that's not going to happen, is it?
No, yeah. Down the line, I think looking at these in situ with electrochemical bias would be great. But I think experimentally it is quite challenging. So here we start in the neat system.
Yeah, yeah.
Gary,
the
if
first-
you want thin films, I mean, I think potentially a pretty straightforward way of doing that is using the azide phosphonate chemistry that we have, where you put down the phosphonic acid. Now, mind you, you have the issue of doing the electrochemistry through the phosphonic acid, but you put down the phosphonic acid, you spin down a film, you cross-link or tether, and then you wash away everything and you're left with just a few nanometers.
Right. So so what you're actually saying is, in order to achieve the ultra thin films, in order to be confident that you're supporting electrolytes getting in there, especially the counter ion that you need, that's how you would do it. But I'm with a film that at the moment with 100 nanometers thick, where's the counter ion? How far does the supporting electrolyte go into the film?
I think that would depend in tremendous detail on the nature of the electrolyte, the solvent, and the
Yeah, I agree.
So I don't think it's a generic answer, right?
It's not, but isn't this a specs, a kind of grand challenge question of specs?
Well, I think it is, but I mean, it also goes back to a question that I've been posing for a while, and that is, we're spending a bunch of time studying PB/TTT as a model case for a hairy rod polymer. And we're talking about specs working on batteries and photo-induced electron transfer for production of hydrogen. And, the question I have is, are we choosing a polymer that has little relevance to any of that? And so then, do we need to actually ask ourselves, what polymers do we need to be using that have relevance to that? And begin to ask, do we want to invest a lot of time on studying those types of polymers versus, PB/TTT? But this is a discussion that's been going on for a couple of years now, and I feel like I yet to be convinced that this is the right system to be studying. It's going to provide us information, but there's a fair amount. Henning Searinghouse published papers about static and dynamic disorder and PB/TTT, I believe, years ago. And so some of what we're doing is reconfirming what I thought Henning had determined in using other tools, but I do think that this is something we need to think clearly about and discuss in the coming weeks. I have to run to group meeting, but this is all very nice work that folks have been doing, and it raises a lot of questions, which is a good thing for a center like this.
All right. Hey, thanks a lot, Spencer and Henry. Nice job. I think we got some good ideas. This talk has been recorded if anybody needs to go back and listen to something. Thanks so much. Have a good week. Jen and I are around if anybody needs anything.
Thanks, guys.